Assalamualaikum warahmatullahi wabarakatuh and good day again. So in the last video, I have discussed with you about estimating the mixtures for liquids and solid, especially in the way how we could calculate the densities, the average densities of the mixture in solids and liquids. At the same time, I've also talked about the mixtures in gas. For example, like if let's say there is several gas in one container, what would be the best way of us estimating certain kind of properties such as partial pressure or pure component volume. In that way, we also learn across with the ideal gas equation PV equals to nRT, all right, in a way that we assume that the gas perfectly behave. Okay, for example, like the gas only hit with the container wall and it doesn't collide with each other. So those are the assumptions that we make in order for us to decide that this is an ideal gas behavior, and therefore we use ideal gas equation. For this video, I'm going to share with you how does the single phase system could be estimated for gas mixtures, especially when the gas is no longer ideal. So we are going to talk about non-ideal gases. At the end of this chapter, you should be able to understand the following, which is the first one is how to estimate properties for non-ideal gases. At which condition that we talk about non-ideal gases, and what is critical temperature and pressure, why and how this info is important to us. Apply the equations of state for non-ideal gases EOS, in which in the previous lecture, in the previous video, I have talked about ideal gas equation. But now we're going to apply equation of state for non-ideal gases. And finally, we're going to discuss a little bit on the compressibility factor and how to use it. So before that, can we think about what would be the assumptions for ideal gas, and how do you think that the ideal gas, when do you think that ideal gas EOS is applicable and not applicable? Okay, so just think for the next 10 seconds. Do you have any assumptions for ideal gas? I think I have mentioned the answer earlier. And why do you think that ideal gas EOS is applicable and not applicable? This is something that we're going to figure out. So as an introduction, the ideal gas is the basis of the simplest and most convenient equation of state. So you know that PV equals to nRT is called as one of the equation of state. It is the simplest and it is the most convenient for us to use. However, okay, at sufficiently low temperature, okay, the keyword here is low temperature, okay, and at the sufficiently high pressure, okay, so a value of specific molar volume predicted with the ideal gas equation can be highly inaccurate. So the level of inaccuracy differs for different species, which means that here, if let's say we have a gas mixtures at a very sufficiently low temperature or at a very high pressure, the gas doesn't behave ideally anymore. Okay, so if you imagine, like, if you're putting people, a lot of people in an elevator, okay, in a lift, if let's say you compare to only have 5 people in a lift, but then now you're putting 15 or 20 people in a lift, instead of 5 people, they may be just holding the wall of the lift, but they may not be holding each other. But when you start to have more people inside the lift, so they are starting to hold not only the wall of the lift, but also maybe they're just, colliding with each other inside the lift. So this is what we call as high pressure, sufficiently high pressure, okay, because they are too tight, they're too compressed in a way that the ideal gas equation does no longer valid. Okay, so another thing is when you consider about the low temperature, okay, very low temperature. So at a very low temperature, then we can say that here, for example, like gas, which is it doesn't work, it doesn't actually um, it become inactive. Okay, the gas become inactive. It also means that ideal gas equation cannot be used for this particular scenario. Several more complex but more accurate equation of state for single species and for gas mixtures, especially when the gas is no longer ideal, will be dealt with in this lecture.